It's my great pleasure to introduce Professor Tsang from Ochanomizu University in Tokyo, Japan, and she's going to speak on Hopf Galois structures of cyclic type on parallel extensions of prime power degree. Please, Professor Tsang.
Okay, thank you for the introduction, and thank the organizers for giving me the opportunity to talk at this online conference again this year. So what I'm going to talk about today is based on this paper that is on the archive, and this is joint work with Andrew Darlington. He's a postdoc at BUB at Brussels. He's among the research group in Lendro van Drammen's research group in Belgium. So the title says Hopf Galois structures. So the motivation comes from Hopf Galois theory, but actually the tools that we actually used are purely group theoretic. So if you look in our paper, it's all group theory, but the motivation is from Hopf Galois theory. So just to start, let me give some background on Hopf Galois structures before going to the group theoretic part. So let's think about what does it mean for an extension to be Galois? So say I have a finite extension L over K of fields, and I let G to be some subgroup of the K automorphic subgroup of L. So L over K doesn't have to be Galois, there's some finite extension of fields. So I have a field K, and then I have a group G, then we can form the group ring KG. And KG is naturally a Hopf K algebra. It is a ring, so it has the usual unit and the usual multiplication. And then you have the co-unit that sends everything in the group G to the identity element. You have the co-multiplication that sends each element of G to the tensor product of the same element with itself. And then KG becomes a Hopf K algebra, where the antipode is given by the map that takes each element of G to its inverse. So you have this group ring that you can form, and it also acts naturally on the field L, where K, it acts via scalar multiplication, and the group G, we're taking G to be a subgroup of the K automorphism group of L, so it acts naturally via automorphism. So one can think of this action as defined by the K algebra homomorphism that takes an element in the group ring to the endomorphism that sends each element X to this natural element that you get, where G acts as automorphism, and then you just take a scalar, you do scalar multiplication, and you take the sum. So this is from KG to the endomorphism group. One can extend scalars, and this yields a natural K homomorphism from the group ring LG to the endomorphism group. It's the same map, you just extend scalars. And this map is always injective. To see why it's injective, each element of G, well, it's a K automorphism from L to L. The zero element is going to map to zero, so one can forget about it. And so one can think of each element in the group G as a character from the multiplicative group of the field over the field L. So by the famous linear independence of characters, that tells us that the elements in G as characters, they're linearly independent over L. And this is exactly means that the map right here, the kernel is trivial, and so it's always injective. Now, what about surjectivity? If we compare dimensions, so the LG here and the endomorphism, right, they're both K vector spaces. As K vector spaces, the dimension of L over LG is, you have the L part that contribute to the degree L order of the group G. And in the endomorphism, the K endomorphism group of L just think of them as square matrices, and obviously the degree, the dimension is the degree of L over K squared. Well, since the map was injective, it's going to be surjective if and only if the dimensions match up. So if and only if the order of G is equal to the degree of the extension. And remember, G was a subgroup of the K automorphism group of L. So the order of G can only be equal to the degree if and only if the extension is actually Galois, and we're taking G to be the entire Galois group. So this perspective, it kind of gives us a different way of thinking, when an extension is Galois. So this observation kind of says that, okay, we can think of Galois as being characterized by the bijectivity of this map phi. So you have an extension L over K, and you have, let's say it's Galois, and you take G to be the Galois group. Then you have this natural action, and this Galois is precisely when you extend scalars to L, you get a bijective map. So the motivation of Hopf Galois theory is to extend classical Galois theory to extensions that are not necessarily Galois. So in that case, you can't take the group ring KG, but then the idea is you replace the group ring by some other Hopf algebra. So you replace KG by some Hopf Galois, some Hopf algebra H, and let's say it acts by some K algebra homomorphism, and you say that it's Hopf Galois when the map that you get by extending scalars to L is bijective. So more precisely, so this definition is due to Chase and Switler in their 1969 book. So if you have a finite extension of fields, a Hopf Galois structure on L over K is a finite dimensional commutative Hopf K algebra, equipped with an action on L via some K algebra homomorphism. There's some technicalities. You want the action to be compatible with the co-unit co-multiplication and multiplication of the Hopf algebra. The exact details is not important. It's just satisfying some compatibility conditions. And then it's such that when you extend scalars to L, the K homomorphism here is actually an isomorphism. So I'm actually not an expert in Hopf Galois structures. If anyone wants to know more about this, there's a book by Lindsay Charles that kind of explains this in much more details. So from what I know, from what I've read from some papers or from some textbooks, the original motivation when they introduced Hopf Galois structure was to study inseparable extensions. But then it turns out that you don't get enough information. You don't really get much out of this approach of using Hopf Galois structures. But nevertheless, the definition applies to any finite extension of fields. So it applies to separable extensions as well, even though the original motivation was to study inseparable extensions. And if we look at finite separable extensions, then there's a very nice classification, a group-theoretic classification of these Hopf Galois structures. So let me briefly explain, okay, how did this classification work? So this is due to Greither and Paregas. So what they showed is that their work applies to all separable extensions, but just to start, let me explain the Galois extension case. So suppose I have a finite Galois extension of fields, and let's say the Galois group is G. Then what they showed is that when you look at Hopf Galois structures on L over K, they're in one-to-one correspondence with these so-called regular subgroups, and in the symmetric group of the Galois group, that are normalized by the left translations. Here, regular subgroup means that the action of N on G is transitive and the stabilizer is trivial. That's what it means. So this is a nice correspondence. It kind of reduces something in Hopf Galois theory to something that's completely group theoretic. And the one-to-one correspondence is also explicit. When given such a regular subgroup, then the corresponding Hopf Galois structure is given by like this. It is also kind of like a group ring, but for the coefficient, you take L instead of K. And then you look at the elements fixed by the action of G. So here G acts on L as the Galois group, and then it acts on the regular subgroup by via conjugation by the left translations. So this gives you a Hopf K algebra, and then the action on L is also explicitly defined. So in the title, it says cyclic type, it's Hopf Galois structures of cyclic type. So the type, what we mean is that when you look at this correspondence, then the type of a Hopf Galois structure is the isomorphism class of the corresponding regular subgroup. That's what we mean by type in the title. So in particular, if you fix some type n in advance and say, then this one-to-one correspondence, well, fixing the type just means that you fix the isomorphism class of the regular subgroups that you look at. So this is a nice correspondence, but it could be difficult to work with sometimes because the symmetric group of G is really big. And you have to find the regular subgroups, and you need to figure out which of them are normalized by the left translations. So instead of using this, there's another result due to Nigel Byatt. What he showed is that if you fix a type in advance, because this is the Greither-Paredes correspondence, what he showed is that down here, instead of looking at regular subgroups of the symmetric group of G, normalized by left translations isomorphic to N, you can look at the regular subgroups of the holomorph of N that are isomorphic to G. So you're kind of reversing the roles of G and N. Isomorphic to G instead of isomorphic to N. But instead of in the symmetric group of G, you look at regular subgroups in the holomorph of N. And the holomorph of N is defined to be the natural semi-direct product of N and the automorphism group of N. So this is nicer because holomorph of N is much smaller in general. Let me just also note that the type that can occur here, it has to have the same order as the Galois group. So it has the same order as the degree of the extension. With this translation, you lose the fact that the correspondence is one-to. So this is no longer one-to-one in general, but it gives you something that's easier to work with. So we didn't take this perspective in our paper, but let me just mention in passing that regular subgroups of the holomorph that are isomorphic to G, it is known that they're related to these things called skill braces, where N here corresponds to the additive group, and then the G here corresponds to the multiplicative group. So so indirectly, there's some correspondence between Hopf Galois structures and skill braces. And this has been made explicit by Stefanello and Topanian. There's a paper that kind of makes this connection explicit. But it's nice that you have kind of Hopf Galois theory, you have group theory, and then you have a skill brace theory. They're kind of different things, but they're all interconnected. Now, so this is the Galois case. Now, what about the separable case in general? So instead of Galois extension, just let L over K be a finite separable extension, not necessarily a Galois. And now I'll let L tilde be the Galois closure. So G still represents the Galois group. And then here, I'll write the Galois group up here to be G prime. So the extension is Galois if and only if the G prime here is actually 1. So the Greither-Paredes, in the Galois case, it says Hopf Galois structures on L over K are in one-to-one correspondence with these regular subgroups of the symmetric group of the Galois group that are normalized by left translations. In the separable case is almost exactly the same. You just replace the G here. Instead of looking symmetric group of G, you look at symmetric group of the left coset space of G mod G prime. And then the correspondence is also explicit and is similar to the Galois case. So instead of L here, you replace it by the Galois closure. And then when G prime is 1, we just get back what we saw earlier. So same as the Galois case, the type of a Hopf Galois structure is defined to be the isomorphism class of the corresponding regular subgroup. So if I fix a type, some type n in advance, then when I look at Hopf Galois structures of that fixed type n, then it corresponds to these regular subgroups that are isomorphic to n. And same as the Galois case, the result of Bayes applies in the separable case as well. The difference is that in the Galois case, you have a correspondence between Hopf Galois structures of some fixed type n and the regular subgroups of the holomorph that are isomorphic to G. In the separable case, instead of looking at regular subgroups, you want transitive subgroups that are isomorphic to G. And you also need to throw in this extra condition. Not just transitive subgroups isomorphic to G, but you need, because the G prime here also matters. So you want an isomorphism so that would take this G prime to the stabilizer. So you need the stabilizer to correspond to G prime. And again, same as the Galois case, the type that can occur here, the order is the same as the index of G prime and G, which is the same as the degree here. And again, this is nicer. This might be a little bit easier to work with than the original Greither-Paregas correspondence because the group here, holomorph, is much smaller than the symmetric group. And just kind of mention in passing that just like in the Galois case, you have this correspondence with scale braces. In the separable case, there's something called scale braceoids. This is the scale braceoid defined by Truman. I think there are two different things called scale braceoids in the literature. What I'm saying here is the scale braceoid in the literature of Hopf Galois structures, not quite. Not the scale braceoid that is recently defined by Yu He. But in any case, you have this correspondence. You look at transitive subgroups satisfying this condition. They're kind of related to this thing called scale braceoids. So again, you have Hopf Galois theory, you have group theory, and you have like scale braceoid theory. They're different things, but they're all interconnected. So this is kind of a rough overview of Hopf Galois structures. So we're going to use this correspondence. This is not one-to-one, but there's some correspondence between Hopf Galois structures and these transitive subgroups. So because of this correspondence, we can study Hopf Galois structures using completely group-theoretic methods. And this is the approach that we're going to take. So what is the actual problem that we want to study? In the title of the talk, it says Hopf Galois structures on parallel extensions. So what do I mean by parallel extensions? So this is a relatively new concept that was introduced by my co-author, Andrew Darlington, in his recently published paper in the Journal of Algebra. So let's say I have a finite separable extension of fields, and same as before, I'll tilde for a scalar closure. Then an extension L prime over K is said to be parallel to L over K if the L prime here is an intermediate field right here. So it's contained in the Galois closure of the Galois closure of L. And you want the degrees of L over K and L prime over K to be the same. So they're kind of, in terms of a picture, they're kind of parallel, because when you draw what's going on, they kind of line up like this. There are just make two remarks here. First, this definition is only meaningful when the extension is not Galois. Because if it's Galois, then the L tilde here is equal to L. So the only possibility for L prime is just L itself. So the only extension parallel to L over K is itself, so you're not doing anything interesting. Also, the terminology might be a bit misleading. It says parallel, but this relation is not symmetric, because according to this definition, you need L prime to be contained in the contained in the Galois closure. So if I look at extensions that are parallel to L prime over K, well, then I need to look at the Galois closure of L prime. But the Galois closure of L prime could be straightly smaller than the Galois closure of L. So L might not actually be contained in the Galois closure of L prime. So in that case, we cannot say that L over K is parallel to L prime over K, even though they have the same degrees. So we need this extra condition. So you have this setup. It seems kind of natural to compare, because they're both contained in L tilde, and then they have the same degree. So maybe there's some relationship between the Hopf Galois structures on L over K and the Hopf Galois structures on L prime over K. So that's what we want to study. Hopf Galois structures and parallel extensions. We want to know how the Hopf Galois structures here compare to each other. There are many things you can study, or you can compare them in many ways. But what we're going to do is to focus about the problem of existence. We don't care how many Hopf Galois structures we have. We just care about existence. So in particular, so let's say I have a finite separable extension of fields, same setup as before. L tilde is the Galois closure. So L prime over K is parallel to L over K. So for example, we can ask, okay, suppose L of K, what I started with, emits a Hopf Galois structure. So it exists. Does it mean that L prime over K also emit a Hopf Galois structure? Just existence. Does existence here imply the existence on any parallel extension? This problem is probably difficult to solve in general. So in our paper, we fix the type. So instead of just admit the existence of any Hopf Galois structure, we fix the type in advance. And we ask, if L over K emits a Hopf Galois structure of type N, does it mean that L prime over K also emit a Hopf Galois structure of type N? So this seems more approachable because we can fix the type in advance, so we just have to work with N. And this problem can be solved group theoretically using the classification that I explained earlier. So let me explain how this problem too translates to a group theoretic problem. So the setup is, okay, I have L over K, which is a finite separable extension of fields. And then I'm going to let L tilde to be a Galois closure. And same as before, I use G to denote the Galois group here. And then G prime is the Galois group up here. The result that the classification and the simplified version, the result of it that I explained. the existence of a Hopf Galois structure on L over K of some fixed type N. Well, these Hopf Galois structures are not necessarily one-to-one, but they're in correspondence with the transitive subgroups of the holomorph of N that are isomorphic to G via some isomorphism that would take the G prime to the stabilizer. So these two statements are equivalent. Now, the question that I want to ask is, the hypothesis is that if L over K emits a Hopf Galois structure of type N, so I assume this hypothesis. L over K emits a Hopf Galois structure of type N, and by the result of it, that means that the Galois group here, it has to be isomorphic to some transitive subgroup of whole N. So that G prime gets mapped to the stabilizer. So in this case, well, instead of taking an isomorphism, we can just identify G as a transitive subgroup of whole N, and then G prime will be identified with the stabilizer. This is the setup so far. I'm assuming that L over K emits a Hopf Galois structure of type N, so I think of G as a transitive subgroup of the holomorph, and then G prime is now the stabilizer. Now I want to look at extensions that are parallel to L over K. So by definition, the extensions parallel to L over K are the extensions that are contained in the Galois closure, and then you want the degrees here to be the same. Well, by the usual Galois correspondence, these parallel extensions correspond to the subgroups of the Galois group of index N. So I take some subgroup H of G of index N. And then now the question is, what we want to know, okay, does it mean that the extension here, the parallel extension, also emit a Hopf Galois structure of type N? Well, to decide whether this is the case, we use the same equivalence and same result of mentioned right here. To see whether it has a Hopf Galois structure of type N, okay, we find the Galois group, and then we see if it's isomorphic to a transitive subgroup of whole N by an isomorphism that takes the upper group here to the stabilizer. So then what we have to do, okay, we're looking at this extension now. So we need to look at the Galois closure of this parallel extension, the fixed field of H. So what is going to be the Galois closure? Well, the Galois closure of the fixed field of H, well, it's going to be the largest normal subfield of L tilde containing LH. So by the Galois correspondence, this corresponds to the smallest normal subgroup of G contained in H. So in the language of group theory, the smallest normal subgroup of G contained in H is what we call the core of H in G. You can or abstractly you can define it as the smallest normal subgroup of G contained in H, but abstractly is you take all the conjugates of H and then you take the intersection. So by computing the core, then that would give us the Galois closure of this parallel extension. Galois closure is just going to be the fixed field of the core. So then now the Galois group here is going to be G modeled out by the core. And then the Galois group up here is H, which is this modeled out by the core C. So by the equivalence mentioned on the previous slide, then we know that this extension, the parallel extension here, emits a Hopf Galois structure of type N if and only if the Galois group here is isomorphic to a transitive subgroup of the holomorph under an isomorphism that takes the upper group, the Galois group up here, to the stabilizer. So in summary, the question we want to study, well, in group theoretical terms, what we do is, okay, we fix the type n in advance. And let's say then we start with some transitive subgroup of the holomorph. And let's say G prime is the stabilizer. This we can do when we assume that the extension that we're looking at, L over K, emits a Hopf Galois structure of type n. Now the parallel extensions corresponds to the subgroup of H of index small n. Oh, in this case, it's the same as the order of the type here. And then for each subgroup H of G of index the order of n, okay, we find its core. And then we want to ask, okay, is the group G mod C isomorphic to a transitive subgroup T of whole n via an isomorphism that takes the subgroup H mod C to the stabilizer. So this is now completely group theoretic. Let me just remark that, so this is problem 2 in group theoretical terms. Problem 1, if we don't fix the type in advance, one can still reduce problem 1 to a group theoretic problem in the exact same way. The only difference is that if we're not fixing the type in advance, then, well, for example, here it could be some n, I don't know, and then if we're not looking at the same type, and we're just asking for the existence of Hopf Galois structure of some arbitrary type, then here, instead of the same group n, we'll have to consider this question for all groups, let's say m of the same order as n. But a priori, if you fix the order, you don't have a characterization of all groups of that order. So maybe it's, except for some specific orders. So in that case, maybe this problem is not solvable because you will have to look at, there are just too many possibilities to look at. And that makes the problem very difficult. So because of that, in our paper, we fix the type in advance so that we only have to work within the holomorph of n for a fixed group n. So just a remark. So for H, if this H is actually in the same odd G orbit as G prime, the stabilizer of 1, so it means that you can find an automorphism group of G that takes H to G prime, then the answer is clearly yes in this case. Because in this case, the core, or the core of the stabilizer is going to be 1 because G is transitive. So the core of H would have to be 1 as well. So in that case, instead of G mod C, we're just looking at G. Instead of H mod C, we're just looking at H. Well, so then we can just take the isomorphism to be the phi. We can take the T here to be just the same group G. It's a transitive subgroup, and it takes H to the stabilizer G prime. So for example, if H and G prime are conjugates, for example, then the answer is obviously yes. But otherwise, it might not, the answer might be no in some cases. So finally, let me introduce the results that we were able to obtain in our paper. So in our paper, so what I've explained so far, it works for any type n that we can fix in advance. So in our paper, we fixed the type to be cyclic, which seems to be the most natural place to start. And we restrict the type, the order of the cyclic group, which is also the degree of the extension, to be a prime power. So in this case, we were able to completely answer this problem too. So if n is cyclic of a prime power order, then we know exactly when the answer is yes. So I'll just briefly explain our main result. And well, same as many cases when we work with prime or prime powers, the prime 2 is always different. And same with our result. The off prime power case and the even prime power case, the statements of the theorems are completely different. But the off prime power case is actually very easy. In that case, this question, the answer to this question, the group G mod C is isomorphic to a transitive subgroup of whole n via an isomorphism that takes H mod C to the supervisor. The answer is yes, if and only if H is conjugate to G prime. So if G is conjugate to G prime, then the answer is obviously yes. And what we showed is that this is the only case you can get yes. Otherwise, if it's not conjugate, then the answer is no. The proof is actually quite easy. We kind of figured it out in a couple of days. And we thought, okay, we can do this. And then when we moved on to the even power case, you kind of hit a major roadblock. It got really difficult. And if you look at our paper, the odd case, let's say roughly, maybe it's only 5 pages. And then the even case took 20 pages to prove. So most of our work was on the even case. So the even case, let me just first give you the statement. So in the even power case, so when n is cyclic of order of power of 2, then we have to kind of break it down into different cases. And we have to break it down. We look at, so H is the same H up here. So this is a subgroup of G, which is a subgroup of the holomorph. So the holomorph was the semi-direct product of n with odd n, so I can take the intersection with the n part. So this, maybe I should write this. Yeah, so the holomorph of n was the semi-direct product of n with odd n. So now G is in the holomorph of n, and H is a subgroup of G. So H, it lies in here. So we're taking the intersection of H with this copy of n in here. And when you take the intersection, well, n, this is going to be normal in whole n. Normal in whole n because we're looking at cyclic groups. So it's abelian, so it's going to be normalized by the n part. And if you have cyclic group, the subgroups of a cyclic group, they're all characteristic. So it's going to be normalized by the odd n part as well. So the H intersected with n is going to be a normal subgroup of whole n. So in particular, it's normal in G. So the core is going to contain this part. So the answer to this question, the answer is no, if and only if one of the following holds. And the case is by the order of this intersection. So if the order of the intersection is at least 4, then the answer is always no. If the order of the intersection is 2, then they're different cases. So if G has no element of order 2 to the E, then the answer is no. And if H is not normal in G, then the answer is also no. Otherwise, the answer is yes. And the last case is when the intersection has order 1. This is the most difficult part. We figure out the exact conditions that one needs. Basically, the order of G has to be 2 to the e plus 1. N is the order of n is 2 to the e, so it's only 2 times that. And then h and g prime, they have to be very specific. And then you have some conditions about g intersected with n or the commutator subgroup. The exact conditions is not so important, but there's just some conditions that you have to impose to get the exact answers. And the notation here, the sigma here is a generator of n, and the phi part here is for phi b is the automorphism that sends the generator to sigma to the b. That's what the notation here means. And in the square bracket, we're rewriting elements in the holomorph of n is just square bracket. So the first component is elements of n, so some power of sigma. And the second component is automorphism of n, so it's phi of b for some b. The reason why you can see the odd part is very, very clean, very easy. But then the even part, you have so many different cases you have to consider, and the statement is quite long. And here are a couple of reasons why the even case is much harder. There are two, I think, main differences. Well, one of them is the automorphism group. The automorphism group of a cyclic group of prime power order, if P is odd, then the automorphism group is cyclic. So it's nice and easy. But if it's even, when the exponent is greater than or equal to 3, then it's not cyclic. Well, I guess, when the order is 8 or more, then it's not cyclic anymore. So it gives you more possibilities. Another thing is that when you look at the transitive subgroups of the holomorph, in the odd case, one can show that a transitive subgroup of whole n has to have an element of order p to the e. So that kind of rules out a lot of possibilities when we look at G mod C. But in the even case, this is not necessarily true. The only thing one can show is that it has an element of order 2 to the e minus 1. So you have to divide it by a factor of 2. That's why it makes the even case, there's just too many different possibilities one can consider, and then that leads to all these maybe seemingly weird conditions. So finally, let me just briefly explain the proof of the if part of this theorem. So if one of these conditions hold, then we want to show that the answer is no, meaning that G mod C is well, this statement is true. It is false. In some cases, G mod C is not even isomorphic to a transitive subgroup, so we don't even need to look at the stabilizer condition. So this is the case when the order of H intersected with N when the order of this intersection is at least 4. And the key lemma we use here is if you have transitive subgroup with a holomorph of N, then it has to have an element of order 2 to the e minus 1. Well, in this case, if the intersection has order greater than or equal to 4, then the quotient group here, it has no element of order 2 to the e minus 1. Because if you raise anything in the holomorph to the 2 to the e minus 2 power, well, this is what you're going to get. And then this part, the automorphism part, is going to be trivial. And then if you look at this part, one can show that the pink part here is divisible by 2 to the e minus 2. But if the order is at least greater than or equal to 2, then it contains this. So then, which is in turn contained in C. So this group has no element of order 2 to the e minus 1. So it's not even isomorphic to a transitive subgroup of whole n. And the same thing holds when the intersection has order 2 and G has no element of order 2 to the e. So in this case, the pink part here, it might not, the pink part here, if B is congruent to 3 mod 4, then it's divisible by 2 to the e minus 1, so which is contained in here, which is in turn contained in C, so it's okay. And if B is congruent to 1 mod 4, the pink part is at least divisible by 2 to the e minus 2. And when G has no element of order 2 to the e, one can show that the V here would have to be even. So then combined together, you would have enough powers of 2 to make it into C. So in these two cases are fairly easy to prove. The other two cases are difficult. I won't go into the details. For this case, when the intersection has order 2 and H is not normal, in this case, the quotient can have an element of 2 to the e minus 1, so we cannot use the same approach. We tried many different things and kind of computed a lot in Magma, and we found this fact that if you have a transitive subgroup that's not regular, then the center has to be cyclic, and then you have this inequality about the size of the center and the size of the commutator subgroup. And then I will skip the details, but basically, if you assume that the answer is yes, then using the fact that this has to be cyclic, you get an inequality for this index. And then using this equality, we get an inequality kind of going in the other direction. So this index is at most 2, but at least 4, so we get a contradiction. And then the last case, also I will skip the details. So in the last case, the C can actually be 1. So in that case, G mod C can be isomorphic to a transitive subgroup of ON. So we need something. We'll need to look at the stabilizer condition as well in order to get a contradiction. And kind of trying different things, we've figured out that the correct thing to look at is look at the centralizers, and somehow look at the size of the centralizer, and show that unless this condition D holds, or when condition D holds, we're gonna get a contradiction, and so it's impossible. Well, I don't think I'll go into details, and I think I'll just stop right here. Thank you for listening.
Thank you very much. Let's thank Professor Tsang for a beautiful and very clear talk. Are there any questions or comments? Well, you spoke about the proof of the if part. Can you say something about the only if implication?
For the only if part, I guess we just construct an explicit. We find a way to explicitly construct the isomorphism that we need.
I see.
Yes.
And that is that straightforward or?
No. It took us quite a while to figure it out, and we made some mistakes. But I think that the final version is correct. It's not obvious at all.
I see. Yeah, that's what I thought. Any further questions or comments?
Excuse me, may I have a question?
Please.
Yeah, so my first question is the Hopf Galois structures, it is a generalization of the classical Galois extension by replacing the group ring by a co-commutative Hopf algebra. So my first question is it possible or meaningful to consider more general Hopf algebra? do not require the property of the co-commutative?
That I don't know. So I study mostly skill braces and the group theoretic part of the Hopf Galois structure. So this I'm not an expert in Hopf Galois theory, but I from the book, for example, I think in Charles' book that I referred to, I think the co-commutative Hopf the other papers, you don't see this. You see this. I'm really sure between us.
Okay, yeah, thank you. Thank you. So my second question is, there is a one-to-one corresponding between the Hopf Galois structures. Yeah. It looks very clear to construct Hopf Galois structures by use of the regular subgroups. So my question is, what about the other side? Yeah, it is easy to make sure what the regular subgroups is by given Hopf Galois structures.
I think
so.
Yes, I think it, one can show that when you have a Hopf Galois structure.
Yeah.
I think in the probably show when you have a Hopf Galois structure H, you tensor it over K with L, then I think what the proof says is, okay, you can find some group and that is so that you have an isomorphism here, and then the type is the n that appears here.
Okay, thank you very much.
Yeah.
Thank you for your talk.
Thank you. Any further questions or comments? Well, if that's not the case, let's thank Professor Tsang once more. Thank you very much.
Thank you.
And unfortunately, the speaker of the next talk is unwell, and so this is the end of this session. So please join me in thanking once more all the speakers of this session. Thank you very much.